This is lecture 47, and we were looking for the adaptation of equalizer coefficient on receiver side. And with that, we saw actually two techniques. One was database adaptation, and this we had seen in more detail so far. And the other one was edge-based adaptation. Okay, so we will look edge-based adaptation today. Do you guys have any questions so far? They can be for the precursor ISI also. No, so whatever, so when I basically discussed the adaptation for the database, right, I did not assume anything as a precursor or a postcursor. You have seen, right, the feed forward equalizer which I was considering, I didn't consider any specific case. So the techniques apply to both. Okay. Anything else? So whatever adaptation techniques I am talking so far, they do not include the clock recovery, how the clock and the adaptation techniques will interact with each other, because this thing is done on the same, which is input, which is coming at the input of the receiver. So we will discuss that thing, but before that, assume right now that you know the clock, you have the clock frequency sampling at a right instant, you are just trying to equalize the received signal. Okay. So the edge-based equalization, which we let me just plot the same thing which I just made yesterday, a very bad eye diagram. And so what we were looking for the information was how this edge, how the edge which I am showing in red is different from a received, say, how the ideal edge is different from the received edge. Okay, so let me just say, so ideally you know that it's for all the data, you should always, the transition point should always be the same in an equalized channel. So in case, okay, this is, so let me consider only one kind of edge, let's say rising edge, right? So ideally the rising edge should always be passing through some intersection point. Here I am marking it as 0. But depending on how the channel ISI is, this can be something like this also, and it can be something like this also. For a transition from bit d of n minus 1 to bit of d of n. This is just for the transition thing. So if I am sampling and my sampling clock is still the same, I am sampling at the, this is my sampling, the edge is my sampling clock. This 0 thing is my sampling clock. Right now I am not changing that. So if I sample a larger value, that means the error is positive. If I sample the lower value, that means the error is negative. Okay. So based on that, if I want to change my equalizer coefficient, so let me just write, this is Cm of k plus 1, Cm of k minus, this is the regular method which we are doing here, which is LMS adaptation also. Now here the information which we are using is the edge information, right? So what do you think is like, what information exactly should be used to change this coefficient? So let me say this, what you are having from here, if you sample at this point, right, your error E of n is, let's say with respect to 0, it is greater than 0. If you are sampling at this point, your sampled error is actually lesser than 0. Okay. So either you measure the exact value of the error, or you can also measure the sign of the error, whether the error is positive or negative. So depending on the positive error, I would basically try to bring this red thing down, right? So I will change my coefficients accordingly. So the update in the coefficient depends on the sign of the error. Let me just, I'm going with the sign of the error. Let's say you're not doing the exact. If you do the exact, that will also be fine. This is of k, sorry. Okay. Now, what other information should I use here? Whether it's, because the way I have shown you, this is only a 0 to 1 transition. Similarly, at the same point, you can have a 1 to 0 transition. And you can also have a case where there is no transition. If there is no transition, you are actually not measuring any error. So whatever, let's say you want to implement in the equalizer coefficient, that should take into account 0 to 1 transition, 1 to 0 transition, and no transition in account. So what can you suggest I can use here to make a update in the coefficient? So let's say I have d of n minus 1 and d of n both with me. Now this d of n minus 1, let's say just we write the bit symbol as minus 1 and plus 1 in place of 0 and 1. So you have minus 1 minus 1 minus 1 plus 1 plus 1 plus 1 plus 1 minus 1. So these can be the positive case. We know that in this case, let's just write it as something as alpha of n. In this case, I should not make any change, right? So this one should turn out to be 0. Oh, sorry. This one should turn out to be 0. Now, if I am from minus 1 to plus 1, so this is the transition which I have shown here. So what shall I use for, if my error is positive, I should reduce the coefficient or increase the coefficient. Assume right now this is a simple gain factor. So I need to reduce the value which I am sampling. For minus 1 to plus 1 transition, let's say you are on the green curve, right? So green curve, if the value is error is higher, I need to reduce the gain factor, so I need to reduce the coefficient. If I want to reduce the coefficient from a minus 1 to plus 1 transition, my alpha n, or let's say this is alpha n, this should be positive 1. Whereas if the transition would have been plus 1 to minus 1, if the transition was plus 1 to minus 1, then you have to do the other way around. It's negative, right? So this is what I need to multiply as alpha n. And changing the coefficient will be by some factor, let's say mu e, delta. So I'm not, no, this is the edge. So this is the edge sampling clock. So when I drew this eye here, right, your data sampling clock is happening here. That is, let's say phi of data, your sampling clock. Whereas your edge sampling clock is at this point, phi of e. So this is, everything is with respect to phi of e, and phi of e is not changing. Okay. So this, now it's like every time I have to compare dn minus 1 and dn, and that's how I will apply this plus and minus 1 for the update of the equation. Okay, this can just be simplified as, sorry, CM of k plus 1 Cm of k mu e. Now I am writing alpha n as sine of d of k minus d of k minus 1 times sine of error of n. You can check this, d of k and d of k minus 1, if d of k is positive and d of k minus 1, if both the bits are the same, this basically turn out to be 0. Okay, 0 is taken multiplied. You're not considering positive sign of 0 or negative sign of 0. And if d of k minus 1, d of k and take is 1, and this is minus 1, then you are having a 0 to 1 transition, then it will be plus 1. Whereas this is minus 1 and this is 1, it will be minus 1. Alpha of n. I'm just replacing that. So this equation can be used to adapt your coefficients on the basis of the error which you detect at the edge. Okay, the thing which we have not talked, if I am going to change the error based on the edge information, how it is going to change my eye opening at the sampling of the data edge. Or if I change at the data edge, how it is going to change at the edge transition. Okay, so actually both will interact, and if you are changing the equalizer coefficient based on the edge, it will reduce the ISI on the data. We will see this thing. It will reduce the ISI on the data, but that sampling edge, but that may not be an optimal sampling, optimal equalization. So there is something in between. So it's not that if you change the edge, you are perfectly cancelling the ISI at the data sampling edge. If you are doing at the data sampling edge, it's not that you will always cancel the ISI at the edge sampling. Okay. So are the two techniques clear? Huh. So this will be this is a good point. This is basically I'm looking for as d of m minus k, and let me just bring it, write it again. You will only look, you will look for the transition as that edge. So let me just get it. Just hold for a second. This d of m minus k, m minus k minus 1. So actually right now, no, this is actually a bit more complicated. So the other one will come slightly later, the exact information. So right now you can just say I'm talking about the gain factor. Okay, what happens in, let me just write it back. What happens in this case is in edge-based equalization that your coefficients are dependent on other coefficients also. So it is not that, so let just a minute, this, let me just put it here, d of k minus d of k minus 1 times sine of error of n, error of k. So what happens in edge-based equalization is any coefficient is actually getting dependent on the previous coefficients or other coefficients, you can say. So that will come when we talk about how exactly the different coefficients are affecting the edge transition. Okay, right now you just take it, this is simply a gain factor for one single coefficient, and we will come to the number of coefficients little later. So in case you have seen that for the database adaptation, right, you see it is only dependent on the current sample or the current bit for that coefficient, whereas in edge it doesn't happen that way. And that will become clear when we consider how the edge is, how the basically these coefficients are affecting the edge values itself. So let's start with that. So one thing here in this case is when you are doing this adaptation, now look at how the clock is changing. So we have to see the clock, first the clock and then the clock with the adaptation. Okay. So let me just bring up. Okay. Let me just write this as a steady state condition in CDR. And then we will look both of these in relation. Okay. So let me say that, let's say this is the input of the CDR. This is the input I, and which is t period wide. Okay, your data sampling edge is here and your clock sampling edge is here. This is a lock condition of a CDR. Even when, so this is the case when I am showing that there is no ISI. Even when you have an ISI, what is going to happen is at the sampling edge, you will sometimes you have a positive and sometimes you have a negative. Okay, so let me start with this. So let's say the response final, whatever the after the equalization or what without the equalization, let's consider the pulse response of the channel as something like this. Okay, so an ideal data sampling point is this, which is the maximum of the I. Okay, and let's consider that your this is the next bit period. So I'm just plotting the roughly scale bit periods. Okay, now let's say this response is our final equalized response is y of, not y, let's use this value as phi of t. This is the pulse response of the channel. Okay, now, and this value is the ideal sampling point t of s, and the next ISI or the bit point is ts plus t, ts plus 2t, and so on. Okay, now now you consider a one bit period across the center point. So one bit period across the center point will be, let's say I am just using as the center of these two. So this is one bit period. So this is ts plus t by 2 and ts minus t by 2. These are the two edge points. If I log to the center of the data, these are the two edge points. Okay. So now if this thing, this input is going into your clock recovery loop, where you are recovering the clock based on the edge transition. Let me ask that so let's say this I is going to your CDR or whatever. Let's say, yeah, the same thing, clock recovery loop. So what is the input here at an edge point? So let me write that as y of t. So y of ts minus t by 2. I'm considering right now the edge point. And why am I considering the edge point? Because I'm saying at the edge point, in a steady state, you will have a mean value as 0. Sometimes you will be positive, sometimes you will be negative. Okay, so y of ts minus 2 will be, so if you feel any thing here, let me know. This is, okay, let's write it. Y of n t plus okay, this is ts minus t by 2 plus nt. I'm just considering like n number of bits you are having. I'm considering that if you, for the nth bit sampling point, the sampling point will, let's say, is nt plus ts. Okay, and then the edge point for that is nt plus ts minus ts by 2. Okay, so that will be equal to d of n into phi of ts minus t by 2. This is due to the nth bit, plus d of n minus 1 into phi of ts plus t by 2. Did you get this part? So the thing is, the previous bit is just this waveform shifted one bit period before. So whatever you are seeing at ts plus t by 2 in this response, that will be due to the previous bit. Okay, plus I have all of like d of n minus 1 minus k into phi of uh, ts plus t by 2 plus kt, and k here goes from 1 to all the values. So this is the value at any given instant. Whenever you are sampling, it will depend on all these values of the previous bits. Okay. Now, if I am locking to a position where this sample, let me just call this as a sample value as y of n. Now, in the clock recovery loop, if you are settling to the mean value of 0, which is expectation of y of n goes to 0. Sometimes you can be positive, sometimes you can be negative, right? Which implies, now look at this thing. If you are having an edge information at any given instant, you should have a transition from 0 to 1 or 1 to 0, whichever. Okay, so let's consider the case when dn is 1 and dn minus 1 is minus 1 for this case, and everything else can be anything, whatever you want. So expectation of y of n is expectation of phi ts minus t by 2 plus phi of ts plus t by 2 plus your d of n minus 1 minus k into phi of ts plus t by 2 plus kt. Okay, now this thing, now consider both the cases. There is no randomness as such in this, right? The only random part in this variable is this d of n minus 1 minus k. And for an equiprobable transmission of bits, d of n minus 1 minus k can be plus n minus 1 with an equal probability of half. So that mean goes to 0. So what you are left with is, what you're left with is phi of ts minus t by 2 plus, sorry, this is minus, right? I told that one bit is positive, other bit is negative for the transition, minus phi of ts plus t by 2. So in a steady state, this should be equals to 0, which implies that I will choose the clock recovery loop will lock to a sampling point such that this will hold. It will become more clear if you see the diagram. Let me just plot it. So this is all on the channel response. So let's consider that you are having, so let me just plot it here. So let's say if the response of the channel is something kind of this, okay, and this is your sampling point Ts, and this value is Ts minus t by 2, sorry, plus t by 2, and this one is Ts minus t by 2. Okay, so in this particular case, what you see, if this is the whole bit period, you lock to the middle of the eye. Okay, whereas if my equalized response is something, let me just say if something like this, this one, and just pick a value that here, and let's say here. So if my channel response is something like this, this is a very bad response I'm plotting, but let's say like this. So then it will lock to a position where, so for example, let's say this value and this value are t by 2 away, sorry, t apart. Then you will not lock to the peak value, you will lock to somewhere in between. It will choose a center point, the negative feedback loop will choose a center point which will force this h to be locked at the center, and your sampling point changes. Yeah. No, right now we are not considering any equalizer. I will come to that. So this is just understanding the clock recovery when it locks to the edge. Okay, we'll come to the equalizer just in a while. Why did we take? No, can you just repeat the question? Mm-hmm. No, so D of n, so what are you, in this case is basically having the random data as an input. First, that is the first thing, right? Now, if the random data is the input and we are looking at the edge information for the locking of the clock recovery. If you are looking at the edge information, you should have a transition. If there is no transition in the system, you cannot lock it. So consider that at a given time instant, you are having a transition, right? And so at a current time, when if you're having a transition, then that is dependent on dn and dn minus 1. They have to be different, right? And it will have a contribution from all other bits. Okay. At another instant, because you're considering the mean, so at another instant, you can also have a 0 to 1 transition, but all other bits can just flip their sign. You get the point? So at one time where you were getting a positive error for a 0 to 1 transition, at another instant, you are getting a negative error. So on an average, the feedback loop will basically lock to like a zero mean of the positive and the negative transitions. Yeah. Pardon? So no, that very much depends on me. So this is very much dependent on a channel response. If the basically for your bit for a given bit period, if the two edge points are equal across the center, yeah. So that this will be maintained means the difference between let me say this difference should be equal to t. Yeah, yeah. Means that is, I'm not violating that thing anywhere. But I can always, it means if you look right, means there is nothing which is telling you that blue cannot be the response of the channel. I'm just placing, so if you are bit concerned, so let me just show you these things. So I have as, let me just mark this point. I have, okay, sorry. So TS, TS plus T by 2 and Ts minus T by 2. Okay. So I can have, I'm just plotting the sample right now. I can have something like this, this, and this. This is when you are equally spaced in magnitude also, and the bit period is T. Okay. In this place, I can also, there is nothing which is telling me that I can't have this transfer, this as a channel response. It just depends on the channel. So the only thing is when you are doing, when this is equalized, sorry, when you are locking the loop with an edge-based thing, you send, it's not always true that you will always be in the center, the peak value. Okay. Now the question is, what happens when you have a DFE or any cancellation which is happening? So let's look at that. How does the sampling point changes with and without DFE? And then we will come to the whole interaction between the CDR and the equalization. So let's say this is the channel response, and let me just mark the bit period here, and let's say something here, and the edge points are here. Okay. So this one. So now Let me ask you, if you are cancelling a first post cursor ISI in this case, what effectively are you? So let me write this also. This is just a minute. This is phi of, let's say, 0, or with a subscript I can write. This is phi of 0, phi of 1, phi of 2. Okay, and this is phi of minus 1. So if I am cancelling the first post cursor ISI, what I am effectively doing is I am trying to bring this down to 0. And how will I bring it down to 0? I will apply a pulse. So this is the whole of your bit period. Let me just write it more detail. This is TS. This is TS plus T. Sorry. Yeah, this is TS plus T. So I will apply a pulse after this some bit period. Let's say this is okay. So if I bring this down to 0, I will surely have a pulse here, right? Cancelling pulse with response to your DFE post cursor coefficient. And that pulse has to rise from somewhere and come down somewhere, right? There should be some point where you rise the pulse and you reduce where you apply the pulse and where you basically take it back. Take it back is like, this is equivalent to, you can say, uh, at this node, what I am doing is I am applying a d of n minus 1 to a pulse waveform at this point. D of n minus 1 is just a bit. You have to basically make it to cancel the post cursor ISI. So if I am now see this, the rectangular pulse with the slope which I am plotting here to cancel the post cursor ISI. So after the post cursor ISI cancellation, what do you think the output, this pulse response will be? It will be something kind of this, right? So you cancel the first post cursor ISI, and what happened to the edge transition? Let me ask now that. That has also changed. But you cannot have just an infinite value at one point. So now if I write this edge, if I'm right now, this is only considering only, let's say I cancel only one post cursor, right? So this condition, can you write now y of n? So see this y of n, we are saying that expectation of y of n should be equals to 0, which is now phi of ts minus t by 2 minus phi of ts plus t by 2 minus dfe, let's say the first coefficient I am cancelling, right? So now this is a very much assumption here that it rises only to the half of the value here. Okay, this can be any, it depends on the slope what you are having. So let me just say it is dependent on the DFE coefficient, and I am considering it rises only to the half of the value. Now this should go to 0 for the locking of the clock recovery loop, which implies now phi of ts minus t by 2 should be equals to phi of ts plus t by 2 minus dfe 1 by in a steady state. So now if I ask that the sampling point in this and sampling point in this, you can see that for the same channel response and everything, my sampling point has changed because they cannot have the same same answer for the non-zero DFE coefficient. So you see, when we were not having any equalization, at that time it locks to this value. Whereas as soon as we have the DFE coefficient, the sampling point change, the locking point change. Now you can say as the locking point change, then the DFE adaptation again has to be redone, right? There will be some difference. So these two things happen simultaneously. They can happen simultaneously in a system. The only thing will be you can have a different loop adaptation bandwidth. Maybe you are doing the DFE adaptation much slower than your clock recovery. Okay, so this is just how the coefficients will vary. Now the case is what happens as a steady state coefficient value with the clock recovery loop. So now we will look that steady state coefficients, steady state equalizer coefficient with clock recovery. So the thing which we are using for clock recovery is that we always lock to the edge where you are having an average of zero for the edge transition error. Okay, so now let's go with the right in case of so I have let me just plot it so it becomes a little bit clear. This is RT and I have an equalizer. Now whether this equalizer is in feedback or anything, that is fine. Now this goes to my clock recovery loop. Okay, and also this value means this also goes to a coefficient adaptation loop. So let's say coefficient equalizer, just write it as equalizer adaptation, uh, just like it. Now this equalizer adaptation values will basically go and tweak the equalizer coefficients, and at the same time whatever clock recovery clock sampling clock you are getting, that sampling clock will go and basically is also getting applied here for the equalizer. So both the things are there in the system. Now, so this is x of t, and let me write this as y of t. And let's consider that we are doing now a data-based adaptation, sampling database adaptation. Okay. So now for a sampling database, what it means is that for the adaptation, I am only looking for the data samples, which you have marked here with red circles here. Okay. So now, and let me just do it for a DFE post cursor. Okay, here. So y of sampling point nt plus ts will be equals to your d of n times phi of ts, and then it will have all the other coefficients which are d of n minus 1 minus k times phi of ts plus kt, and k goes from 0 to all. Is this equation all clear? Because you are just basically adding up the post cursor ISI from the. So this is only adding the post here. Yeah, I didn't show you any this thing. I did not show you any DFE in this particular case, right? But now, if you are having a DFE, now can you tell me what will be the. So can you modify this equation if you're having a DFE in a system? Let me ask just that. So this one is without DFE. So if I write with DFE, what do you have? You have d of n phi of ts. So just look at this waveform. So here, the post cursor ISI, whatever you are getting, so d of n minus 1 minus k phi of ts plus kt minus, let me write dfe of k, right? For the previous bit, No, this is right now I'm assuming that I'm not, I mean, whether it is fully cancelled or not, I'm still not writing it that. I'm just saying that the post cursor ISI, which is caused by the previous bit, is dn minus 1 minus k into phi ts of kt. Okay, and we are trying to cancel that ISI with dfe of k, and at the data sampling point, there is only one cancellation happening. Okay, so with dfe, just write it as, so this is the input which is going to your DFE coefficient adaptation loop. Okay, and if you remember, what were we trying in the DFE coefficient adaptation loop? Whatever after the cancellation is, we are trying to compare it. So I think you, if you remember that if this was going to a comparator for a DFE adaptation loop, we are trying to get the error from here, right? This is what we were doing before. And this then error is used for the coefficient adaptation. So this is like you are comparing y and t plus ts with some reference level. Okay. So let's say if that reference level is the same as phi of phi ts, which is the maximum value here, and dn and dn minus 1 are there, all the bits are plus minus 1, that during coefficient adaptation, we tried that the mean square error minus, I'm just saying for the bit, let's say this square should be minimized. This is the error. The inside is an error, and we try to minimize the mean square error. And then that information was used to adapt the coefficients. Now we are just asking that in a steady state, what should be this value turn out to be? Pardon? So phi of ts is the peak sample point. So I am just putting a level there. So earlier what I was comparing all the equalized value with respect to plus minus 1. Okay. Now I am saying that plus minus 1 is just getting multiplied with phi of ts. Whatever the peak value you are getting, I'm just maintaining that as a level. I want that. Else there is only a gain factor. There's nothing more than that. So this is what the equalizer would demand. That the mean square error should go to 0. Pardon? Yeah. So y of you are saying is basically depending on whether dn is plus or minus 1. Yeah, that's fine. Okay. But in this case, this is only the equalizer part. The other part is what we are, because we are also locking the clock. So what is happening at the clock? So let's see, y and t plus ts minus t by 2. Now this is a bit more involved equation. So at the edge, I have d of n phi t, d of n, yeah, phi ts minus t by 2 plus d of n minus 1 into phi ts plus t by 2, okay, plus now d of n minus 1 minus k. Now what comes here is something which you need to look. So look at this. Okay, so for the second post cursor, what do you think will happen? So what I have drawn is, let's draw that again. I think that will be much better. So all these are edge points. Let's say this something here, and all these are edge points. Yeah, data points and edge points. Okay. Okay. So for cancelling the first post cursor ISI, we had, let's just apply again also to this. We had some kind of this pulse, and the coefficient of this pulse was DFE1. Okay. Now for cancelling the second post cursor ISI, which is basically this. So let me now plot with a different waveform. You will have to cancel this one, right? DFE2. Similarly, for cancelling the third one, you will have something else. Okay. Yes. This thing. Now you just think that if I am considering the edge at this node, let's say this is the data edge, right? So what all things are happening? What is happening? So this is the edge thing, right? So I will just basically bring all these things for an I means on average I am looking at, right? One time one thing happen, other, because you're considering all the previous bits. So consider what is happening due to all the previous bit at an edge. Okay, so this will be phi of Ts plus T by 2 plus Kt minus dFe of K plus dFe of K plus 1 by 2. So let's look if this equation is right. So for K, this is greater than 1. Okay, so at the second edge, look at this edge, you are having a DFE of 1 and DFE of 2. Both you are trying to subtract at the edge. So this is the edge information which you will have. Sorry. Yeah. So when we are adapting for a database equalization, at that time you should have for the edge information y of nt plus ts minus t by 2 should be equal to 0. Yeah. So the thing is, the equalization is data based, right? But the clock recovery, both the things are happening. So the solution should be a common solution for a steady state. In a steady state, the equalizer, whatever the sampling point you choose, that sampling the coefficient as per that sampling point should also have something in common, that that sampling point should be enforced by the clock recovery loop. So that's why I wrote here. So I got this edge information, but in this particular case, the edge information is true for the clock recovery. Okay, so right now I'm not considering the mean square error at the edge. I'm only considering the mean of the error, whatever value I'm having at the edge, that should go to 0. Okay, so where is it? Okay, let me just write the equation number. So that would be, excuse me. Yeah, anything? So let's, pardon? Yeah. So arrow mark is, so you are considering, let's say, at any given edge, right? Now at that edge, you will have a contribution from the previous bit. So the way I showed here is that at each edge transition, you can have a DFE1 plus DFE2 contribution. Did you get that part? So, okay, let's plot it. And so let's say this is the one which you are considering. So let me just put it like this. Okay. And what happened due to the previous bit? So let me just mark that too. Let's say here and here. And this one, this one. So this is the previous bit, right? The one in the blue. Now for the previous, so if you are cancelling the post cursor ISI for the previous bit, what are you doing here? Let me just say this is the edge. Sorry. If my current bit is this, TS, what you are doing with respect to the previous bit, you are cancelling ISI, right? Now consider another case where you have this, okay, this point comes here only, center point. So, okay, let me just mark it here and something here. And this one, let's say this. So this is the dn minus 2 bit, right? Okay. So what are you going to do at dn minus? So dn minus 2 contribution at the sampling point should be cancelled, right? So what I do, I basically, so let me just plot some away. So for dn minus 2 bit, I am cancelling the post cursor ISI at the TS sampling edge, right? For the dn minus 2 bit, I would be at an instant TS minus T, I would be cancelling the ISI for the previous bit. So what I was doing, so this is DFE2 second coefficient, and for this particular thing you are having, for cancelling this, you are having another, for cancelling the ISI for the previous bit. You get this part? Okay, so what happens at the intersection as due to dn minus 2 bit? You get a coefficient, you get a DFE1, DFE2 plus DFE3. You got this right? No, so for the, no, this is not like for, this is DFE1 plus DFE, sorry, DFE2 plus DFE3 is only for the previous, sorry, the second last bit. So this is what I showed here, right? So let me just mark it again. So consider that for the green one, which this is dn minus dn, this is dn minus 1, this one is dn minus 2, right? For the dn minus 2, to cancel the second post cursor ISI at the dn location, you have to cancel by DFE2. But for dn minus 2, to cancel the first post cursor ISI at dn minus 1, you have to have DFE1 on that. But both are going to contribute at the edge of dn. So when I write, so if you look 5ts t by 2 plus kt, k is basically here, in this case k goes to 1, right? And the bit is dn minus 2, and which all DFE1 and DFE2 by 2 contribution. Yeah. There is a coefficient of? Yeah, so there, this is dn minus 1 is already, so you have this one, right? DFE 1 by 2. Yeah. Okay. So this is the, so from here we want that the error information should go to 0, and from this error information going to 0 and the mean square error for the at the sampling point due to for the coefficient should be minimized. So these two things will lead to you, so you can say there is a common sampling point. So if you make, let me write this as equation 3 and this one as 2, no, this is not this one. Okay, yeah. Let's say this is 1 and 1a. So 1 is a general equation, but for the adapting coefficient, we have to minimize the mean square error, that is 1a. And this is the second equation, that is the edge information. And for a database adaptation, the edge information, the mean at the edge error should be equals to 0. So a common solution will exist between 1a and 2a. The TS sampling point should be chosen such that a common solution exists between the two, and the final DFE coefficient should come with respect to these two equations. Pardon? In this case. So the other case is where we want, so the other case is where the edge error will basically be minimized. That will be E of y and t plus ts by 2 uh, minus, sorry, plus ts minus t by 2. Now this is the error with respect to, so this is the just the edge error we are calculating. This error should be minimized. So let me call this as equation 3. Mean square error goes to 0 in an ideal case. Okay. Then for a edge based adaptation, 1a, sorry, you are having a clock recovery also, right? So 2a and 3 should have a common solution. Database, and this is edge based. Yeah. Let's stop here.